name is Jeff Hammond, and I work for the NVIDIA HPC group, and I'll be talking about NWChem on ARM, 7 years and going strong. Of this talk is as follows. I'll talk about what NWChem is. I'll talk about NWChem's history on ARM processors going back a few years. I'll talk about some experiments with different software configurations on the ARM Altra Q8030 platform. I'll do a comparison of the ARM Altra Q8030 with an Intel Xeon 6148, which is a Skylake server, and I'll talk about some conclusions in future work. NWChem. So if you don't care about the details, it's a widely used open source quantum chemistry code. If you do care about the details, it's a project started in the 1990s with the goal of running well on all major HPC platforms. Life was both simpler and more complicated back then. It was simpler in that all of the processors, or the vast majority of the processors, were CPU-like, and the architecture was relatively similar. On the other hand, it was before MPI-1 existed, and it was before Linux was widely available or used in HPC settings. And so what that meant was that NWChem was designed to be platform agnostic by abstracting away the OS, the processor, the I/O system, the network, etc. So there's a lot of stuff in NWChem that doesn't make sense anymore because we just use MPI and Linux everywhere. But NWChem was engineered to be agnostic to any sort of system even before MPI and Linux existed. As a result, NWChem is remarkably architecture agnostic across CPUs and has never had a problem with running on new CPU architectures. So not surprisingly, ARM turned out to be pretty darn easy. NWChem is millions of lines of application code, primarily Fortran with a little bit of C. About 1 million lines of Fortran were written by human beings. There's about 3 million lines of generated Fortran. So, the generated Fortran is both easier and harder to maintain. It wasn't written for human consumption, but it turns out to not be very, very critical as long as it compiles. And this is, generally speaking, legacy Fortran. It's not punch card era Fortran, but it's also not using modules and polymorphism and type user-defined types and all that fun new stuff that's now part of Fortran. There's also about 100,000 lines of C to deal with the system, including memory allocation and I/O and the network and the like. It used to be that the primary bottleneck for running NWChem on a new system was porting ARMC to that network. Of course, now that MPI is ubiquitous, there are a variety of ways that ARMC can just use MPI, and so this isn't really a bottleneck anymore. There are a couple of different backends. I'm going to compare two of them in this talk. They're not really that important. They don't make a huge difference, but it's still worth comparing them just to make sure. So the first one is MPI-PR. That's one of the conduits. It's the best conduit to use on most systems in the PNNL distribution of ARMC. It comes with global arrays. PR stands for progress rank. It means it dedicates a core to driving the network. As you'll see later, if you run on 10 cores, it's going to compute with 9 and use 1 for the network. So you'll see a little 10% artifact. Of course, on 80 cores, 79 out of 80, not really noticeable. It doesn't make a difference. It's also that this core that gets used turns out to have tremendous value in distributed systems because it drives the network and makes sure that background progress is made on all communication operations. That's tremendously important to NWChem. ARMC MPI is another implementation of ARMC that works with global arrays. It's not shipped as part of global arrays. It's a standalone project. You can install it NWChem as a script to install it automatically. And it uses MPI-3 RMA directly. If the RMA library does a really good job, ARMC MPI performs great. If the RMA library stinks, ARMC MPI doesn't do anything about that, and it stinks. So these are just different design trade-offs to explore. It turns out in shared memory, it doesn't make a whole bit of difference. So the performance characteristics of NWChem are primarily dependent on the linear algebra library, the BLAS, if lots of BLAS calls are being made. In the experiments we'll talk about here, it's not a lot of BLAS calls. BLAS performance doesn't matter. The performance of MPI matters a great deal, and if basically you'll notice if MPI is behaving badly. If you're getting poor bandwidth or you're not making asynchronous progress somewhere, NWChem definitely notices that, and that's why MPI-PR dedicates that core to work around MPI libraries that don't do the right thing. Fortran code generation sometimes matters a little bit. It's not a dominant effect in most of the code. And the OpenMP runtime, if we were running a module that had OpenMP support, that might be noticeable too. neither of those things are really big factors here. So what we're going to see is a primarily compute-bound application with low sensitivity to the software properties. If you want to know some more details, there's a talk I gave a couple years ago at NERSC about the design of NWChem's software architecture, if you want to read about that. To the best of my knowledge, the first ARM platform that NWChem ran on was an NVIDIA Kayla board that we had at Argonne. We got in late 2013, and I think I must have ported NWChem to it over Christmas vacation that year, and I wrote some of my now NVIDIA colleagues about it on the 2nd of January 2014. So that was basically the first time that NWChem ran on ARM, and as we'll see, it wasn't that hard at all. And it is, of course, particularly fun for me to be at NVIDIA now and to be part of doing this NVIDIA ARM server stuff for real with NWChem. Porting issues that existed in 2014, if you could even call them issues. So no source code changes were required to any part of the NWChem application. If there was a build system flag change, something like that, I don't remember it. In those days, the only Fortran compiler for ARM was GCC. Worked just fine. Obviously now there's a number of other ARM compilers, including Flang, open source, and ARM's Flang, and then Cray's Fortran and Fujitsu, etc. NVIDIA's Fortran as well. But in those days there was one, and it worked. So that's what we tested. For the BLAS, Netlib and Atlas both just worked. Bliss and OpenBLAS had some very minor software issues. Bliss had a funny issue where it didn't work for 3x3 matrices. That was fixed in a day. OpenBLAS was compiled for a different FPU ABI than NWChem was, and they were incompatible, and that meant that you got the wrong answers. That was an easy thing to fix, but all of these issues have been resolved for 7 years now, and haven't affected anybody else. Global arrays, back in those days, I don't believe that the ARMC that PNNL was shipping had ARM assembly language support everywhere that it needed it, or at least I didn't try it. ARMC MPI was just written straight to MPI, and therefore we used MPitch, and MPitch supported ARM in those days, so it just worked. So I don't know if PNNL ARMC worked or not. It didn't matter. For something as small as a Kayla board, the MPI performance was irrelevant. So in those days, even the very first time, 7 years ago, ARM porting was trivial. That was the 32-bit ARM system, and as we'll see, there really isn't any difficulty that's changed. NWChem on ARM in 2021, nothing bad has happened. So it works out of the box on all the Linux ARM64 platforms I've tried. I assume ARM32 works, but I haven't tried that in a while. So I have run NWChem on a Rock Pro 64, Raspberry Pi 4, Raspberry Pi 3, a Xavier AGX from NVIDIA, and I run on Apple M1 on a regular basis. For the M1, there was one compiler flag that needed to be changed from being SSE x86 specific to not, and there was one line for changing to support Apple Accelerate, which wasn't even ARM specific. That was just Apple Accelerate specific. Currently, I am able to run with GCC, ARM, and NVIDIA compilers on all the ARM systems that I have or that I've tested with that. There's an issue with the Fujitsu Fortran compiler. I'm not 100% sure whose fault it is. I'm inclined to think it's a compiler bug. It relates to I/O statements and impacts input file parsing. So obviously, I can't really make any progress if I can't parse an input file in NWChem. Haven't revisited that one in a while and don't intend to. I had some issues on Isambard with the Cray ARM compiler stack because I tried to load the compiler and MPI didn't work with it, and I haven't debugged that. I don't even know that that's anybody's fault other than it's just a weird module configuration. The compiler may work fine, MPI may work fine, but it didn't work perfectly, and I didn't have time to debug all of that stuff myself. So most likely Cray Fortran will be fine, but until tested, it's hard to know for sure. So on math libraries, so Netlib, OpenBLAS, Bliss still working. I have problems with Atlas. I don't care about Atlas anymore, but it probably doesn't work unless on some ARM systems, mainly because it's not aware of all the recent ARM chips or something. ARMPL works just fine. I've used that on A64FX, and Apple Accelerate works, of course. On some of the A64FX systems I've used, the Cray libsi is trying to invoke a ThunderX2 object file rather than A64FX one. It doesn't work. Somebody needs to update that somewhere. Presumably Cray libsi will work, or maybe it works already. It just hasn't worked the last time I tried it. And for Cement, which is an atomic integral code that targets vectorization, has some neat support for outer loop vectorization on x86 instruction sets. And Hua Huang, who's the developer of that package, has committed a patch for, or the fix, update for SVE. It just doesn't deliver a significant performance delta versus Neon ASIMD. So there's clearly an opportunity there to improve the performance. Variables in any NWChem study, you're going to have compiler optimizations for the atomic integral code and anything else that's going on with Fortran. Math libraries, BLAS, LAPACK, math.h, libm type stuff, sine, cosine, exp. In these experiments, turns out none of that stuff really matters. NWChem works around exp, doing its own quadrature or its own numerical evaluation there. It's faster, slightly lower precision. Eigensolver turns out to be not a bottleneck in the DFT simulations I've running in this talk. So I run OpenBLAS everywhere. I also compared against NetLab. It didn't make a big difference, and therefore you can assume it doesn't matter. Global arrays, ARMC, and MPI makes a little bit of a difference. What we're seeing is a shared memory performance impact in RMA. OpenMPI is a little bit better than MPitch. What we see is the MPI PR design of stealing a process for progress, which is a really good idea in some cases. Of course, when you're running on 10 cores and only computing on 9 of them, you see a 10% effect. Obviously, that's intentional. There's no flaw there. It's just part of the design. ARMC MPI doesn't by default have that design, so it runs 10 out of 10. So you'll see a little bit of a difference there. Doesn't really matter. None of the simulations I'm running here have any I/O bottlenecks, with the file system. But if you run NWChem in such a way that you grind on file I/O, what you do see is some impacts of serialization of the I/O through Linux to local disk. I'd love it if that wasn't the case, but in general, it's just better to run with a lower process count and try to avoid those Linux bottlenecks. Talking about today involve a dual socket Ampere Ultra Q8030 server. That's an 80 core per chip, 2 socket system, 3 gigahertz maximum frequency. So there's a 3 gigahertz part that's a little higher performance, obviously, but it probably doesn't make a huge difference here. So the compilers and math libraries I'm using the built-in GCC 831 that comes with the system. I know that there are new versions of GCC. They might make a small difference, but what we see here is less than 10% performance difference from the Fortran compilers. NVIDIA HPC Fortran does a really great job with a lot of code. So if the difference between these two is small, I don't expect GCC 11 to really make a big difference. I'm using OpenBLAS latest with GCC I built myself, and I'm using OpenBLAS that ships with the NVIDIA HPC toolkit. Again, I don't expect this to make a difference. OpenBLAS works, and if performance matters, it'll do a good job. So I used MPitch latest, OpenMPI latest. If you want to know what get hashes I use, you can ask me. It's not going to make a big difference. It's not important dimension to this problem, but it is what it is. Global arrays, ARMC, I use MPI PR and ARMC MPI. Again, if you want to know all the particular details, you can ask me. Out of band, whatever. So if you're a chemist or you just care about the details, I'm going to run B3lip CCPV-TZ. This is a pretty large basis set for B3lip. It's just a way to make sure these calculations actually do some interesting computation. B3lip is the most common DFT functional. So density functional theory is going to evaluate some atomic integrals, form a Fock matrix, diagonalize that matrix. There's going to be an exchange correlation quadrature component in there. It's kind of like, evaluation of functions over grids. Most of this is compute bound unless something's going wrong. The linear algebra is not a bottleneck. So in general, up until the limits of the algorithmic scalability and strong scaling this is just compute bound stuff. And we see pretty good scaling until you get, the wall time gets under 5 minutes, and obviously you're running out of parallel work to scale. If you want to reproduce some of the experiments, you can use my input file generator. You can find on GitHub. It generates benchmarks for this sort of stuff. And it's useful for scaling studies. Okay, so the experiments. First set of experiments here this is 21 water molecules, B3lip triple zeta. You're seeing 8 sets of 5 bars. So the 5 bars descending are 10, 20, 40, 80, and 160 processes. So obviously 160 is filling the entire node, and less than that isn't. I don't expect NUMA or bandwidth to make a huge difference, so I let MPI do the placement. It may have spread them out. It doesn't really matter. These are compute-bound simulations. If one was undersubscribing nodes, there are ways to tune this. I chose not to do that. What you see here are 8 different experiments where there are 2 different MPI libraries, 2 different ARMC implementations, and 2 different compilers. In general, you see a very small difference between those software configurations. As previously mentioned, ARMC MPI uses 10 out of 10 cores and MPI PR uses 9 out of 10 or 79 out of 80 or whatever it is. And so for low core counts, you see about a 10% difference. That's exactly what you'd expect. Out at 160 cores, it doesn't make any difference at all that one of those cores is driving the network. What we see here is that OpenMPI is a little bit better than MPitch for shared memory RMA, and the NVIDIA HPC compilers are a little bit better than GCC for Fortran code generation. But in general, they're all scaling well. They're all delivering within 10% of the same performance of each other, and obviously the benefit, the performance characteristic is dominated by the core count, which is of course what you'd like to see in a scalable workload. All right, performance analysis details. So 2 to 7% difference in the Fortran compiler. This is about what I'd expect from any other compiler comparison I've done in the past. GCC 8 may not have all the Neoverse optimizations. Maybe it's worth 5%, maybe it's not. OpenMPI, sometimes it's about 20% better than MPitch, sometimes it's 0% better than MPitch. It doesn't make that big of a difference, depends on scale. I didn't look at all the parameters. Both MPI libraries have quite a few tuning knobs. With MPitch, you can use UCX or OFI. I chose to use OFI. OpenMPI has even more tuning flags. I haven't figured them all out. Again, you could probably make the needle move a little bit, but it's not significant. ARMC MPI versus MPI PR differs by about 10% either way, depending on what scale you're at, how much value that one core that you pulled out is. And of course, I studied this because MPI PR is going to scale better if the network isn't doing the right thing with the MPI backend. ARMC MPI can work with something called Casper, which you can find out about on the internet. I didn't test it here because it doesn't matter for shared memory. But Casper also can use one or more cores for the network. So in some limit, you can make these things behave the same. It doesn't really make a difference. They're both good implementations with different trade-offs. All right, so here's a comparison of ARM versus x86. So this is the Skylake Xeon 6148 part, which is a little bit older than the ARM system I'm looking at, but there haven't been many changes there in a long time. It's a 20-core part. Obviously, you can get a Skylake or a Cascade Lake with 28 cores, so you can go up a little bit higher. ARM Altra also comes in 128 core part now. So 80 is not the max, 20 is not the max. So yeah, there's 4 times as many cores on an ARM server within a similar power envelope and a similar frequency. So obviously, if the workload scales as it does, ARM's going to win by quite a bit, in fact, depending on how you look at it. But for low core count, Xeon has higher single-threaded performance. So if you only run on 10 cores, Xeon wins by a noticeable amount. If you run on 20 cores, Xeon wins by a little bit less. If you run on 40 cores, it's a wash. And if you run on 80 ARM cores versus 80 hyperthreads, ARM wins. And if you run on all 160 cores, ARM wins by a lot. So here we see an obvious advantage of the power and area efficiency of ARM architecture over x86 architecture. And if you can fit 4 times as many cores at a higher frequency in a similar power envelope, in a similar server design, you're going to win pretty nicely with HPC. In these experiments, I use the same NVIDIA compilers, OpenBLAS, ARMCMPI, and OpenMPI. They're slightly different versions of the compiler because of when I compiled the 2 different binaries. It's not going to matter at all. As we've seen already, compiler code generation is worth no more than 7%. Two different NVIDIA compiler versions 3 months apart is not going to make a difference. And I did the experiment, netlib versus OpenBLAS doesn't make any difference. So obviously if BLAS doesn't matter, adding in MKL is not going to change things significantly. And because there's such a small difference between the NVIDIA compiler and GCC, I wouldn't expect Intel Fortran to make a big difference here. The code in question is not going to get AVX 512 vectorization. Probably not going to get AVX2 vectorization. So it really doesn't matter what the software configuration is. I just picked one that was clearly viable on both systems. So what we see here, there's a clear advantage to the ARM server platforms. And, if you run on the latest x86 system from AMD or Ice Lake, again, you have half as many cores at most as what the ARM Ultra, or the Ampere Ultra system offers. So, unless those cores are twice as powerful, and we're not seeing that here, more cores is better. Conclusions and future work. As expected, NWChem runs out of the box on all the ARM systems and depends only on ubiquitous HPC software like Fortran, BLAS, and MPI. Based on my experience with BlueGene in the past, if NWChem works, pretty much all the computational chemistry codes are going to work. They all depend on the same thing. They all have the same type of algorithms, same type of IO, same type of whatever. And therefore, NWChem is a nice banner carrier for the community. Obviously, if you have a C++ code, you're going to have a different set of dependencies, but we know already C++ works just fine on ARM, so there shouldn't be any problems there. The ARM Neoverse N1 cores in the Ampere Ultra Q80 deliver similar but not identical performance to Skylake Xeon. Obviously, having a significantly larger number of cores makes a bigger difference than having a slightly higher IPC in an x86. Of course, if bandwidth matters, the Ultra server delivers significantly higher memory bandwidth than the x86 platforms out there, and does so with much lower power per core and comparable power per socket. So if you can fit 4 times as many cores in the same socket with higher bandwidth, there's very few cases where that's not going to win. We see compiler quality. NVIDIA HPC compilers win by a small amount. Doesn't make a huge difference. Again, the compiler opportunities are small in this case. B3lib is not going to make BLAS calls. There's not a lot of eigensolver stuff going on in here. In other modules of NWChem like CCSD parentheses T, we'd expect very strong dependency on the BLAS library and probably higher dependency on the Fortran compiler, and we'll look at that in a future study. Finally, SV optimization opportunities in Cement are going to make a big difference relative to Texas someday. Texas is an integral code 20 to 30 years old. It's a really efficient code, but it's not vectorizable and it's not thread safe. So, as soon as we get into the limits where vectorization matters or where we want to do threaded Fock matrix construction, we're going to want to switch to Cement away from Texas. But for now, Texas is better than Cement on ARM chips. On x86, it's the other way around by a little bit some of the time. But again, this is an opportunity for future work in the SV space. So thank you for attending my talk. Sorry I can't be with you in person. Hopefully someday. If you want to ask questions, make comments, throw virtual tomatoes at me, you can find me on the internet. Twitter's really good. You can tweet at me or DM me, whichever you prefer. You can send me email. If you want to, you insist, you can use LinkedIn. LinkedIn's not the best, but if it's an easy way to find me, so be it. So please, feel free to interact. Let me know what you think. Ask questions. If you want any of my scripts, I've automated all this stuff. I can send you all the details, all the Git hashes, all the log files. If you want to go through that, if you want to work on other experiments, if you want ideas for things that you might be able to do with ARM and NWChem and HPC in the future, feel free to reach out. I'd be happy to talk about that. Thank you very much.